to bring up my other screen here first so I can see the presentation. There we go. So welcome to today's meeting. This is a super exciting time for us. I'm Steve Peterson. I've been asked to introduce our speaker today. Lina Martinez is a wonderful person and a great scholar and a good friend. Lina, I first met as she was doing work at NREL 3 years ago, I think it was, and she's been involved in system dynamics in the context of future energy systems. Today, she'll be talking about her work on sustainable aviation fuel, and I'm very excited about this. So Lina, let's take it away here.
Thank you, Steve. Well, thank you for attending my presentation. This is part of my dissertation presentation on system dynamic model approach for policy analysis of sustainable aviation fuel. My system dynamic advisors have been Steve Peterson and Addison King. So let's start with a little bit of background. So the aviation sector is responsible for about 2% of the carbon anthropogenic emissions. The sector, as well as the governments, have been trying to decarbonize the aviation sector, and for so they have a series of measures. One of them are the technological measures. There are some economic measures, but the core has been focused on the fuel that it is used. Due to the emissions produced from the fuel are basically 80% of the total emissions of the aviation sector. Up to now, worldwide, the use of sustainable aviation fuel is only 0.01% of the total aviation fuel consumed. For the production of sustainable aviation fuel, there has been 7 pathways approved under the ASTM, but only 3 of them are commercial or are approaching a commercial state. The one that is currently commercial is hydroprocessed ester and fatty acids, well known as HEFA, that basically use all type of lipids for the production of sustainable aviation fuel. The second one is Fischer-Tropsch, produced with gasification normally, and the third one is alcohol to jet. When we talk about supply chain, we are talking about a series of steps that are needed to transform a raw material into a final product. For the sustainable aviation fuel, those steps are collection of the feedstock, logistics, pre-processing, conversion, distribution, and end use. All this chain is focused on the energy content of the sustainable aviation fuel and is the way how it is valorized. For so, one of the main goals have been having a sustainable aviation fuel that is price competitive with its fossil equivalent. To establish a supply chain, there is a need for a regional perspective due to the availability and the degradability of the feedstock, but also because it is required that the carbon footprint of the renewable fuel is lower than the fossil fuel. But also there is a need to have an investor's perspective. It is important to make sure that they see a business opportunity in the supply chain. There are 3 steps to establish a supply chain: configuration, design, and analysis. There has been a lot of work on the design portion. However, there is always, the configuration needs always to be first. The configuration step is the conceptualization and identification of goals that the supply chain needs to have. Now, there are different supply chain paradigms that depend on the supply uncertainty and the demand uncertainty. Based on the literature on renewable fuels and specifically on sustainable aviation fuel, the move here. Sorry, this was out. Okay. The sustainable aviation fuel and renewable fuels starting from a risk hedging perspective due to it is an evolving process, and they have been trying to move to a lean supply chain, basically because that is the supply chain for all the fossil fuels. They are commodities and they are a stable process. So the aim has been to reduce the cost to make it feasible compared to the fossil equivalent. However, the value proposition of the renewable fuels is focused first on the renewability of the fuels and second on the environmental and social benefits that it can provide. Thus, it needs to kind of transition to a green supply chain that is the one that value those attributes, the environmental and the social attributes. In that case, the price of the sustainable aviation fuel will be affected for the cost of its production, but also for the revenues that the supply chain provides from the other products and co-products, but also from the services that are provided when establishing a supply chain. For example, emission reduction, better air quality, water quality and quantity, waste reduction, among others. Traditionally, the customers for the sustainable aviation fuel and in general of renewable fuels have been the users of those fuels. Aviation sector for sustainable aviation fuel, marine and heavy transportation for the renewable diesel. But under this concept, we have a big amount of corporations and governments that would be interested on the services and the products. So we did a brief check on the modeling and simulation approaches that have been used for the configuration, design, and analysis of supply chain. So for the design and analysis, we have tools that provide high geographic specificity, and the analysis is done mainly in years or months. Due to those are the period of the scope for those analyses. When we are talking about supply chain configuration, we need a higher view. We need a systemic view for that configuration and a longer period of time for the analysis. System dynamics is one of the tools that provide that sort of analysis, and it's the one that we use in this dissertation. So as a way to evaluate the impact of services on the services in the revenue of the sustainable aviation fuel and the configuration, we analyze policies and programs available for sustainable aviation fuel in the US. So some policies are private policies that are part of the sustainability goals for those corporations, and some policies that are federal, state policies that are in aim with the country's goals with respect to different international agreements. As a case of a study, we use the production of sustainable aviation fuel from municipal solid waste using gasification Fischer traps. So to start, municipal solid waste is composed from different materials. In this case, for the production of sustainable aviation fuel, we are only using paper and paperboard, wood, and plastic. Here it's important to notice that plastic is a non-biogenic material, and we cannot claim emission reductions from this material. It has a high carbon content, so it increases the yield of the sustainable aviation fuel conversion. The municipal solid waste also includes glass, aluminum, and steel that we are using to as part of recycle to support the financial part of the sorting facilities. As metric, we have the net present value. This metric is The primary tool for cost-benefit analysis is typically used to assess a project viability and in reference to the amount of exceeding or falling behind an investor's perspective return when the opportunity cost of capital measures the expected return. So the model is a financial model that has 5 modules. The core one is the financial analysis, and in this module we have 2 sets of analysis: the net present value of the project and another one that we call the net present value metric, that is an annualized net present value. The feedstock metric, it contains the availability of the feedstock and it's integrated with the transportation cost in a very high level. It is not detailed, like counting how it is expected to be in the design part. Treatment, prevent treatment, processing, and conversion module includes the virtual construction of the facilities with 3 years for the design and construction, and then the online facilities. Revenues and incentives is all the logic associated with the different policies and programs, and also the revenues from the sale of the fuels. In the CO2 emission reduction module, we have a tracking of the emissions associated with the core of the sustainable aviation fuel production at its supply chain. These emissions are quantified based on the CORSIA method. So here is a representation of how the net present value metric looks in the model. So where we have here a financial scorekeeping, that is what we call the net present value metric, is the annualized net present value, which is affected for the annual discounted cash flow, that is this stock over here, and the net annual revenue, and also here the equity investment corresponding to the normal formula for the net present value. The preprocessing and conversion part, we are assuming then as a kind of 2 facilities that in the other side of the fence. So to start a facility, we need to have a positive net present value. So the magnitude of the net present value is going to affect the time, like how fast the facility is created. Depends also on the availability of the availability of the feedstock and the number, in this case, of landfills that are in the region. Here is the rest of the logic, and it has the accumulators of the plants, the time for design and construction, and then the facilities when it comes online. So the policies and programs that we are analyzing are policies and programs that are applicable for sustainable aviation fuel in the United States. We divided them based on the approach of the policies. So we have tipping fees and loan guarantees as the risk approach, because the aim of these policies is to reduce the financial risk of the investment. Have low carbon fuel standard, the one from California, the one that we are using in this case. Sustainable Sky Act, that is a proposed blender tax credit for sustainable aviation fuel that is running now in Congress. Payment for carbon reduction or carbon offsetting. This is a private program, and these 3 have as goal the reduction of emissions. As production-based policies, we have renewable fuel standard, gasoline blenders tax credit, diesel blenders tax credit, and producer blenders tax credit. It is important to mention here that the renewable fuel standard, even it is mainly a production-based policy, it has some emission criteria. Now, the currency for the transactions under the renewable fuel standard are RINs. The RINs applicable for municipal solid waste and sustainable aviation fuel are T7, which are cellulosic RINs with an emission reduction of 60%. That is the criteria. However, there are not prices currently for T7, so we are assuming the values of D3 that are other cellulosic RINs as the price for T7. So here, the first analysis that I am presenting here is net present value metric and the time that the facility is required to reach a net present value of 0. So when no policies are applied, the investor is basically in total loss. When there are the risk policies applied, there is a reduction, small reduction in the negative part of the net present value. However, when emission bases are included, we can see that large facilities that are 310 million liters per year go to positive, the same as the medium facilities that are 155 million liters of distillate fuels per year. But the small facilities that are only 70 million liters of distillates per year cannot pass that to have a positive net present value. When we analyze the production-based policies, all of the sizes of the facilities reach a positive net present value. However, the greater impact is when all the policies are stuck. That is when we can see all the facilities reaching a positive net present value. On the other hand, we see that the time to reach a positive net present value varies based on the policies applied. So when we have all the policies stacked, the net present value becomes to be positive between the 3rd and the 4th year. When just production-based policies are applied, for the largest facility, it is at the 6th year, but for the smallest facility, it is basically at the end of its production lifetime, that is the year 20. When we think about from a lean perspective, we are always taught that by increasing the yield is that we are going to reach like better income, higher income. So we did that analysis by increasing the amount of plastic that is available. So when we increase the amount of plastic in the feedstock from 3% to 20%, we see how the net present value increases slightly. And all of those reduces the 60% of emissions, so they are under the D7 rates. However, when we increase the plastic in the feedstock to 25%, the emissions reduce are lower. So they just reach 50% reduction. Thus, the RINs that are applicable are D5, which are the RINs for advanced biofuels, which price is smaller. So the smaller price for RINs, the less emissions that you can have in transaction under the LCFS, and the lower payment for the emissions reduction under the sustainable aviation fuel blenders tax credit reduce the net present value that the project can perceive. And the same occurs when we increase the plastic to 40%. In that case, it's not only the reduction from all the other programs, but the DC rings has an even lower price than the D5. So as we can see here, there is a need to align the increment of yield, but also the emissions that we are reducing. So both are as important. That is very important to have a high yield, but that is very important to keep the emissions that have been reduced. The time where the net present value reaches zero also is affected. So it is the opposite. The more plastic that we have in the feedstock, the longer the time that is needed to reach a net present value of zero. Now, this also affects, just a second that my battery is running low and I forgot to have it. Okay, so these policies also affect the development of the supply chain in a region. So here we analyze landfills in the northwest of the United States. So we are assuming that a small landfill has the feedstock to feed a small conversion facility. A medium landfill has the feedstock for a medium-sized facility, while a large landfill can feed one or more large facilities. When we have just production-based policies, the model gives a positive net present value basically in the year 21 of the simulation, and it virtually creates two medium-sized facilities. When we stack all the policies and programs between the year 5 and the year 6, we have a positive net present value that triggers the virtual creation of large and medium-sized facilities in the region. In this case, we can see how stacking all the policies speeds up the virtual creation of facilities in the region. Now, all the analysis was done from a deterministic point of view, but there is a lot of risk associated with the establishment of the supply chain. There is technical, energy prices, and policies and programs uncertainty. So as technical uncertainty, we include fuel yield, capital cost, fixed operating cost, and process feedstock. To do that, we use a Monte Carlo analysis, and the probability distributions were selected based on the available data. Most of that data fit a uniform distribution or a beta birth distribution. For the price uncertainty, we have the price of jet, and we correlate that for the price of gasoline and diesel. We have uncertainty on electricity and natural gas. The analysis was done using a geometric Brownian motion, which is a method to forecast prices where it starts from the past price, has into account an expected growth rate and a random component of how it could behave. For policy and programs uncertainty, we have two: value and duration. So renewable fuel standard and low carbon fuel standard were analyzed on its value under a Monte Carlo approach. We have also the price of the carbon offsets. We analyzed to $50 per ton of CO2 reduced and $150 per ton of CO2 reduced. And we can also change the value from the sustainable aviation fuel blender's tax credit due to it is still running in Congress. So we just wanted to see how much could it affect. On the other side, we analyze the duration of the blenders and producers blender's tax credit, because basically those credits have been kind of on and off during some time. The Congress says that is until one date, and then when that date comes, they approve an extension and they are paid retroactively. So when an investor is assessing this, they really want to know how many years they need of this type of policies for them to invest. So here we have a tool integration. So Stella has already the sensitivity analysis part, but beta PERT is not one of the functions that are available directly in Stella. What we did was randomize the numbers in R and then use the external parameters to have those values as an input and run them in Stella. And actually, that is that helps in the computer time. It reduces the time where the simulation is performed. As an example here, I have the variation in rates. So this here is the histogram for the three prices from 2015 to 2021. So technically, well, when we look at it, we can see that it's kind of a bimodal distribution. However, when running the analysis, it is a uniform distribution. So that uniform distribution we use for the base scenario. That is this line here in the middle. The probability of a negative present value at the end of the plant's lifetime, which means at the end of the 20 years for a medium-sized facility, that is the one of 155 million distillate liters per year, is the 64%. But when we analyze just the prices that is kind of here in the low range, the probability of a negative present value increases to 80%. This is not moving, okay. Increases to 80%, that is here. When we analyze the kind of high in this area prices, the probability of a negative present value reduces to 46%. Now, because we saw before that the higher impact is when all the policies are stuck, we analyze that scenario having a carbon offsetting of $50 per ton of CO2. In fact, at the end of the plant's lifetime, the probability of a negative net present value is lower than 10%. That can give some space and good like signs for investors. But to wait until the last year for them to return their money, it's a long time. So when we analyze the year 10 of production, only the large facility is the one that has a probability of a negative net present value lower than 10%. And none of them reaches that low probability in the 5th year of production. So as conclusions, we have that system dynamic tools are versatile and that they can be used for practical applications along or with other tools. Renewable fuels do not fit entirely into a single supply chain strategy classification, but the green paradigm is the one that is the closest. Ecosystem and social services need to be included in the business model for renewable fuels, and there is a need for valuation of those services. policies and programs that reduce CO2 emission through by goal or through a criteria are the ones that have a substantial impact in the time and the magnitude of for a net present value. Profit maximization requires an alignment of production yield and environmental services. Regional deployment of sustainable aviation fuel production requires the stacking of various revenue streams. The feasibility uncertainty can be reduced through policies and programs, and large facilities have the lowest probability of a negative net present value, but they require an abundant feedstock and a substantial capital. Any questions?
Agreed. Very nice. Nicely done, Lina.
Thank you.
I did have just a couple of questions.
Sure.
And excuse my ignorance on the topic. I certainly have not immersed myself in jet fuel. On the municipal solid waste, what is what's being harvested? Is it methane or what's being captured from the municipal solid waste?
The solid, so for this project, we are assuming that the municipal solid waste are sorted basically on the field, the houses, on the places, and from there the paper, wood, and plastic is selected to go to a gasification process. That gasification basically has a oxygen source or air and high temperature and produces something that is called syngas. That syngas is basically CO and hydrogen, and then it goes to a Fischer-Tropsch process, which uses a catalyst that kind of put these molecules together to form like a line of hydrocarbons that are from the length of a sustainable aviation fuel, but also can produce what is renewable diesel, renewable naphtha.
Very good. So now that I have some grounding, technical grounding, the other question I had was about the stakeholders, specific jet fuel manufacturers today. Are they funding any of the research into biofuels? How do they participate in your model? Where is their influence felt?
Well, this particular project was not funded for any producers. There are some producers that have been participating in other research. Some of them, or most of them now, are producing sustainable aviation fuel from HINFA. World Energy in California is one of them. But they have been also participating in other research from the different national labs, the universities, and ASCENT, that is the aviation center, basically.
So there is involvement by the producers.
Yeah, there are some level of involvement.
And I guess my last question was, could you discuss a little bit more the influence of policy? And I assume by policy, we're really talking about legislative initiatives to allow for incentives and regulations. Can you describe a little bit further what your model, the importance of policy in affecting net present value?
Sure. So there are two ways how we see it. So here, one is the magnitude of the net present value. During the time that the net present value becomes positive, So basically how steep the return of that investment is. And the other part is the objectives of those policies. So different policies that have some alignment with environmental services are the ones that here are making us transition from a perspective that is just focused on increasing the amount of sustainable aviation fuel that is produced to a kind of a pivot point where I really need as engineer to look for the amount of fuel, but also the emissions that our fuel are generating or that are being reduced compared with the sustainable aviation fuel. So that is kind of the key part of those policies here, and how those policies can be seen as a kind of a external valuation of the services that are provided.
And the stacked solution is the accumulation of all the preferred policy.
On all the policies. So the stack one is the accumulation of the risk, emission-based, and production-based policies.
Very good. Thank you. Very nice presentation.
You're welcome. Any other question?
Elena, I have some questions too. Just like Joe, I'm not very familiar with this topic. And so I'm just thinking about the logistics. So right now, you know, the MRF, the material recovery facility, they get the, you know, single stream materials, and then they sort out, you know, like papers and plastic and things like that. But you're saying the municipal solid waste, so I'm a little unsure. So is this from the trash bin or is it from the recycling bin?
So we are assuming a single stream municipal solid waste, so from the trash. We have in the financial part a sorting facility, and they divide the recycling, they divide the papers, they divide the materials that go to the landfill. What is used for the production of sustainable aviation fuel is specifically paper and paperboard, wood, and plastics that are not sold for recycling. Like, because normally like these heavy plastics, they will not go to the sustainable aviation fuel production.
Okay, so this is from the trash bin transported to the landfill, and then another party would sort it out.
Yes, so we are assuming that the conversion facility and the sorting facility are located like in the area of the landfill.
Okay, so that's the new investment from the landfill.
It can be a new investment for the landfill.
Okay. And then you say there's a depot system. So from separate landfill, then the material will be transported to a more centralized location?
So all the trash, we are assuming to, we are leveraging on the supply system for the landfill. That is why we are locating these facilities in the landfill sector, in the landfill area. So basically, instead of just taking the truck directly to the hole for the landfill, the truck goes to the sorting facility. The sorting facility will select the material that is going to use next door for the conversion facility, and the rest is now directed to the landfill.
Right, but I think in one of your slides, you have the depot thing. So that's why I'm Yeah, the feedstock depot facility potential.
Those depots are the landfills.
Okay.
So it's the number of landfills that can host those facilities. So for example, we have 3 small landfills, which means there are going to be 3 small facilities, or 2 large landfills, and they have actually a capacity to host more than 1 large facility. Those are these depots,
Okay.
the landfills.
And so is this still hypothetical, or this is for the entire US? So like the number of landfill, does it match with, EPA? So EPA has a list of different landfill and their size. But that's for the entire US, but in your model, it's not clear that. Is she still on?
I think we may have lost her. So I think Lena's working in sort of Pacific Northwest region.
Okay.
And I think that diagram is basically tracking the status of landfills with respect to whether they have conversion operations located on them. So you could seed that with maybe 10 landfills in the very first box, and then they kind of move through the system as investments occur.
Okay.
Sorry,
You're
lost
there
you guys for
again.
a long second. Yes. Sorry,
Did I
I'm
get that
here.
right, Lena?
I couldn't hear properly.
Okay, so I was just talking about how great you were. So
For what it's worth, I just toured a waste recovery center just about a month ago. I'm located in New York State and in Ulster County, and so we have a recovery center. And at that recovery center, what happens is the organics are separated for composting purposes. The plastics and glass that's recyclable, are separated for their own recovery. And then everything else goes into solid waste, and that gets trucked to a landfill in Seneca Falls. And assume that that's where at that facility, at that kind of facility, assume that's where you would establish the capture of other materials that could be used for the biofuels, versus at the recovery center. So I'm not sure where that facility would be located, at the early recovery stage, or no, all the way at the actual landfill facility.
We're assuming all the way down to the landfill specific, because at least in the Pacific Northwest, those recovery centers are now close or relatively close to the cities. And we will have a permitting problem if we want to locate a chemical plant close to one of the main cities. So
Yeah.
that is why we are assuming that all the process goes down to the landfill, where we have enough land and not much neighbors. So the permitting is not a problem.
So Lena, how much does 1 gallon of this fuel cost?
We are not analyzing here minimum selling price. We are assuming that the fuels are sold at the same value that the fossil fuels. So we are not giving it a distinctive price, rather that the kind of asking for the services. It's a different approach.
Okay.
So in a sense, if you're looking at the net present value calculation, I think
There's a revenue flow, yeah.
Yeah, it's treated as a revenue flow.
Mhm.
Lena, I'm wondering if you did any sensitivity analyses with different discount rates, because I think Fisher-Tropsch conversion is like really capital intensive. And so, you know, depending on if you have a high versus a low discount rate that you're applying, that is a real implication for, you know, for how much you value the revenue stream coming from all of this.
I didn't do it, so that is definitely a good thing, and it's high capital intense. In fact, I didn't do any variation in the discount rate. I was just trying to follow the harmonized perspective from the Ascent group, so kind of be on agreement with them. I just kept the same discount rate, but that is something that could be done.
And did you look into the cost structure of this fuel? Because I'm thinking, you know, if we know what's the most contributing factor, maybe we can find a way. So instead of increasing the revenue stream either through more tipping fees and other mechanisms, we could also try to minimize the costs. You know, because say right now we're trying to sort the MSW, but say if we can use paper from recycler, right? They already pack every sort and bale everything into big stack. And if we were to use that material source, would that reduce the cost of this fuel?
In fact, feedstock cost is an important part in the cost structure. Here we analyze the average cost from the United States and also for the Northwest, which actually have a higher recycling average than the rest of the country. And locations that are not recycling could decrease the whole cost of the project, as because they will see more revenue streams from the new recycling facilities rather than the ones that are already embedded in high recycling facilities.
Okay.
So one of the things that really struck me is the curve that you showed, you know, with the different bar graphs as you increase the plastic content within the within the feedstock flows coming into the system. And you know, it sort of hit me that, wow, that's pretty weird initially, but then it made sense to me, because essentially what you're showing is the kind of the relative contribution of the carbon in the plastic versus in the more renewable paper and wood products, I guess, and you're not getting RIN credit, I guess, from the plastic part. Did I get that right?
You are right. Yes.
Okay. So that strikes me as really important, you know, an important kind of finding with this, because you could make a lot more fuel, but you're not going to help the environment out if you do that, right?
Mm-hmm. You are not going to help the environment, and you are not going to help your finance, because part of this, everyone wants to reduce emissions.
Yeah.
Allison, you're very quiet.
I think
Allison's holding her questions for Friday, right?
I think most of them have been answered. I'm just trying to get my brain. I've just finished 4 defenses and I'm trying to get my brain back into Lena's.
Oh, man.
So,
Oh.
yeah, I was only supposed to have 3 and I ended up with 5. I thought the PhDs were going to go to the fall, but no. Yeah, it's a interesting, and I've sort of, so she's taken, when I've sort of worked with her a bunch, it was more on just getting the configuration of the model set up, and this whole economic analysis is sort of, I really have to think hard about it. So
It's kind of cool. It's kind of cool
Yeah,
stuff,
it
I
is.
think. You know, one of the things that I think, Lena, that you may want to think about in the thesis defense is just really trying to delineate how you're doing the net present value analysis. Because essentially there's kind of 2 ways to do that. One is to say, okay, I'm going to project a bunch of costs and a bunch of revenues, and that's going to condition my decision on whether to do this stuff. And I think kind of what you've done is you've turned that around a little bit, and you've said, you know, let me put some facilities in place here, and let me understand, if I put this in place under these circumstances, let me simulate what the revenue streams might look like, and show what the net present value would be for that. So, you know, you can simulate a facility that is a real dog, you know, that just doesn't make any money, and so forth. And that's what's showing your less than 0 net present values. I think to provide a little bit of context around that may be helpful.
Yeah, and one suggestion from the beginning, if you can say a little more about your system battery, say you only look at the Pacific Northwest, and you know how the sorting and feedstock converted. I think for a general public, like not a lot of people understand that.
Thank you.
So I did have a thought as we were talking about the landfills. In New York State, one of the issues confronting us is, well, running out of landfills, filling up the landfills.
Yeah.
In fact, the Seneca Falls landfill is sort of forecasted to be full in 2040. And so minimizing what goes into our landfills would extend the life of the landfills. That cost avoidance, right, of having to create new landfills, is that expressed anywhere in your model, the avoidance of creating new landfills?
No, really. So, because in this part, actually, we don't have that problem. We have a huge amount of land and landfills that are going to be closing in 2100 and something else. So that part, we are not including it. We kind of just did a rough check from the other landfills, and that could be like a good thing to assess, but for this region was not applicable.
So,
Yeah,
so it'd be interesting to explore that because New York State actually does have an abundance of land. We actually have a lot of land, but nobody wants a landfill in their community. So even though we have physically have the land, there's real, there's no community.
A lot of pushback.
A lot of pushback. So
Yeah.
that's why as we now look out on the horizon to say, well, when will Seneca Falls fill up? Where would you go to next? As you can imagine, everyone is saying, not in my backyard.
Mm-hmm.
Yeah.
Yeah, Joe, I agree with you. I'm working on a project to sort out flexible plastic packaging. And for the New York and Pennsylvania area, saving landfill space is a real need. So Lena, maybe it's not for the Pacific Northwest per se, but maybe you could have that mechanism in there for other regions.
Yeah, I think there may be a slide in the presentation. I'm just thinking, how do we get you a PhD out of all of this, Lena, right? And so to anticipate that question, which Allison's written down and she's going to ask you probably. Allison is not responding, so we'll just let that go. But you might create a slide that says, you've looked at these sort of outside of the economic system benefits. There's a whole bunch of other benefits, and among those might be things like the opportunity cost associated with I think that's the right word, of not closing landfills. That's a big issue in eastern states where you have just more people and more backyards that people would not want their landfills to be put into. And there's probably 2 or 3 other sort of avoided cost categories that you could put in. That would be really interesting because that's going to make the clients for this work, the folks at Ascent and so forth, be really interested in engaging you after you got your PhD as well. But I think that would sort of set things up for future research.
Yeah, I was thinking like a next step slide on that.
Yeah.
And it also gets into the ecosystem services. I mean, I think you can tie that pretty tightly of, out here, you're going to be retiring farmland or grazing land for landfill. And there certainly is a cost.
Yeah.
And to
The
water
boundary
quality.
conditions, right, the boundary conditions of what you've analyzed. The question is there outside of the boundary, is there some boundary parameter that if you change that boundary parameter, well, you could end up with a much different outcome in terms of present value, because the cost of creating a landfill somewhere could be astronomical. Well, maybe not astronomical, but a very large.
But huge.
Can be very. Thank you.
Hey, nice work, Lena. It looks like we're at the hour's up here, and Ruby's going to cut us off in a second. I can sense it. But nice work with this. This is really fun.